Okay. Do you want to get started? Yeah, we're a little after actually. Yeah? Okay. So let me see. I'll give you a little intro. So Laura, what's your last name? Rabbit? Okay, great. Laura Rabbit is going to be speaking on decarbonizing with steam methane reforming for blue hydrogen production. She works with Emerson. Laura was originally an Egyptian citizen prior to becoming a naturalized U.S. citizen in 2017. Laura is a chemical engineer working for Emerson in Boulder, Colorado. She is currently a marketing manager for Measurement Solutions as a subject matter expert for refining and sustainability. Prior to working for Emerson, Laura was a permit writer for the Division of Air Resource Management, the air permitting headquarters for the Florida Department of Environmental Protection. Laura has dedicated her career to the environment by supporting sustainability initiatives with a passion for economic empowerment and innovation. Thank you.
On steam methane reforming, which I'm going to refer to as SMR, and identifying the challenges and solutions, and then lastly going through an economic assessment. I do have several slides in this presentation, so please save your questions. So, need for decarbonization. The United States has re-entered the Paris Climate Agreement. And along with other countries, now there's been emphasis on decarbonizing emissions and exploring new energy markets. In fact, the global demand for hydrogen is expected to reach almost 12 trillion by 2050. And feedstock natural gas for blue hydrogen production primarily. There are other methods with coal. But because of the natural gas supply in the United States and Canada, blue hydrogen production is very prevalent in North America. So Emerson has products that cover the full value chain of hydrogen production. We have an ebook on green hydrogen, which is through electrolysis. We won't be discussing that today. We'll be focusing on steam reforming and primarily using natural gas as the feedstock for that. So I'm also going to go over the end use of hydrogen, specifically for industrial applications, even though they could be used for fuel cells and to produce ammonia. Okay, so refineries are the largest consumers of hydrogen. They consume about 57% of the demand. Mostly the hydrogen is supplied as a byproduct from the heavy naphtha reforming process. And this balances out with the SMR process, which currently is primarily gray hydrogen. So the difference between blue hydrogen and gray hydrogen, carbon capture portion. If you add carbon capture, that is then categorized as blue hydrogen. And so I grabbed this chart here from the International Energy Agency. You can see here, refining consumes most of the hydrogen supply, as well as other industries. And then the bar next to it shows the world areas that are consuming the global hydrogen demand. All right, so moving along, refining. Fossil fuels will likely be the source of hydrogen production with carbon capture, not electrolysis. And biofuel production will also increase the global hydrogen demand because renewable diesel requires more hydrogen than traditional diesel processing. And there's also state incentives for biofuels. California is the leader in this, and Oregon, Washington, and British Columbia are also following those incentives as well. So Emerson has measurement products for the production portion, transportation, and hydrogen dispensing. For blue hydrogen, it's not shown here, but you can also use a density meter as well. But I will be covering that in another slide. So let's talk about the blue hydrogen production process. So aside from steam methane reforming, there's autothermal reforming and partial oxidation, which I refer to as POX. And I won't go into detail on that, but SMR is currently the primary method for producing hydrogen, but right now, gray hydrogen. So don't assume that mostly it's blue hydrogen. It's certainly gray. And natural gas is the main methane source for the hydrogen produced by industrial facilities and petroleum refineries. So here I've compared the SMR, ATR, and POX process. You can see the carbon feedstocks and also the catalyst required for thermal POX. It's non-catalytic. But what's really important to know is the hydrogen content in the syngas. SMR having the largest percentage, approximately 70%. And ATR is commonly used for large hydrogen production processes, but SMR is still the most prevalent. Yes, and all of these three are hydrogen production. Yes, so natural gas would not be used there. It's only for the SMR. Correct. And then also for SMR refinery gas and naphtha, can be used as feedstocks as well. And another thing to note for SMR and ATR, the additives to natural gas, the odorant additives, like the sulfur compounds, can poison the catalyst. That's another issue. Right, so let's identify challenges and solutions. So for fuel switching for combustion sources, you have increased instrumentation, safety issues, metallurgy needs need to be evaluated because of hydrogen embrittlement, flame detectors, and increased NOx emissions. So for hydrogen diffusion, it's not atomic hydrogen, but it's atomic hydrogen that's the issue, not necessarily molecular. So atomic hydrogen can diffuse through the separation membrane, as you can see this diagram here. This can happen in high pressure, high temperature applications or hydrogen sulfide fluorides are present. So what can assist with this is having a gold-coated diaphragm on the pressure measurement converters or diaphragm seals. So this is just some pictures of the gold-coated diaphragms that we have. And then for high static pressure applications, we have a large portfolio for differential pressure multivariable transmitters. Here we have a new product that can go up to 1034 bar, the Rosemount 3051 SHP. And then for relative and absolute pressure transmitter, we have a new product that can reach 1379 bar. Okay, so to address hydrogen flames, which can be invisible, generic detection devices shouldn't be used. It honestly gives a false sense of security. And so for that reason, we have the Rosemount 975 HR hydrogen flame detector, which can detect flames from 300 feet and 80 horizontal and vertical detection range. Yeah. It's invisible. Yeah, it would be transparent. So until it, completely we catch fire to other parts of the process and then question. So safety is an issue with hydrogen production, and so that's why we have this flame detector here that has a high immunity false alarm. at least from far distances, it would be difficult. So this is from 300 feet. So looking at this is an overview of the SMR process here. This example is using natural gas as a feedstock. Then you have your water and gas shift reactor. Downstream of that, that actually increases the CO2 content prior to being captured. So we're going to go through each step of this process flow diagram, talk about the instrumentation used throughout. Okay, so first let's talk about the production challenges. So hydrogen purity is a challenge as well, and energy consumption, as well as safety, which I've mentioned before, and also we want to reduce downtime and maintenance costs. This is primarily focusing on the SMR, where we've identified the instrumentation you would use, so the flow transmitters and the analytical equipment as well. Talk about these in detail. But first, let's talk about the common threats for steam reformers. So it would be high temperature variability, improper steam to carbon ratios, flame instability, high tube wall temperature, high excessive air and flue gas, and combustion air deficit. So for the steam to carbon ratio, this is an issue because natural gas is 70 to 90% methane. You also have methane, butane, and propane. And so changing the feedstock quality leads to challenges in controlling the steam to carbon ratio. And I've included here a table where you can see the pounds per steam per pound of hydrocarbon of methane, ethane, propane, and butane. So we would suggest a Coriolis meter, specifically micromotion Coriolis meter for mass flow, because the mass ratio is much closer to molar ratio than volumetric. By using this, you could extend the catalyst life, decrease energy costs, and increase safety. For gas analysis, you want to monitor the feed gas and intermediate streams, the final products. So we have the Rosemont Continuous Gas Analyzer at the bottom, and the Rosemont 700XA, which is the blue device on the very top here for monitoring the reforming and shift converter efficiency. For hydrogen flow, you could use differential pressure, vortex, Coriolis, or ultrasonic meters. Vortex meters are commonly used for hydrogen applications because they offer fewer leak points. And here we have pictured the quad vortex meter. Emerson's the only one that offers this device for enhanced safety. And for custody transfer applications, we would suggest the Coriolis or an ultrasonic meter. And understanding not only the application, but the process conditions can help you figure out which type of flow meter you need. So for water flow measurement, specifically boiler feed water, you want your feed water to be of high purity, so low conductivity. We don't want to use a magneter for that reason. So we would suggest the vortex meter, specifically the 8800 multivariable vortex meter, which has a built-in temperature sensor. So this removes the need for additional gaskets and seals compared to other designs. For airflow, to maximize the air to fuel ratio in the reforming furnace, we recommend the Rosemont 80 bar flow meter with 485, 585 averaging pitot tube, pitot traverse, which provides 1 to 2% accuracy. And so optimizing the air to fuel ratio will assist in reducing NOx emissions. So for our carbon capture challenges, the main challenges are economic. Overall, that's what these bullet points are getting to. Energy consumption costs. So to lower costs, we would recommend the micromotion density meter. to manage the amine makeup, because the density meter infers rich or lean amine quality to automate the solvent quality process, sampling process, so you don't have to do manual sampling. We've also, once again, identified the instruments that you would use throughout the amine treating process for carbon capture. And you could also monitor the pump and heat exchanger performance as well using Plant Web Insight. In addition, you would use corrosion sensors, which also have Plant Web Insight applications as well. And so the amine treating process is, corrosion is very prevalent due to the carbonic acid attack in water condenses, when the water condenses. We have actually a few sensors in our booth. If you'd like to check them out, speak to our product managers. They are at the 4C conference. And then moving on to gas analysis for carbon capture effectiveness, we recommend the Extreme Enhanced Continuous Gas Analyzer, which is pictured below here. Right, so hydrogen purity is very important because that's the final product. We would recommend the CT5800 continuous gas analyzer for simplified installation, operation, and maintenance, thus lowering operational costs. So economic assessments. So utilizing the CO2 once it's been captured, that would help in making blue hydrogen a more competitive method for decarbonization. Also, other design modifications have been considered. Recently, sorption enhances steam reforming with carbon capture has been reported as one of the strategies to overcome the challenges with the conventional steam methane reforming. And I have my sources here if you'd like to review them as well. So I want to talk about the Inflation Reduction Act, which has incentivized hydrogen production. And this provides credit values from 12 cents per kilogram to $3 maximum, which is often achieved by green hydrogen in electrolysis. Please don't misread this graph here. These credits are not based on the production methods. It's based on carbon intensity. This is just the average carbon intensity rates for these production methods. Okay, and here, this is comparing different world areas. The operational expenditure as well as the capital expenditure. As you can see, it doesn't matter which part of the world you're in, the carbon capture portion, that's the costly part of the blue hydrogen production process. The other thing to consider is natural gas prices. The United States has been very fortunate compared to Asia and Europe. As you can see here, this graph just goes up to February 2022. This is the latest information I was able to get from the International Energy Agency website. And the natural gas usage, 6% of natural gas is globally used for hydrogen production. And then at the very bottom here, I have some comparatives on natural gas costs. Hydrogen production costs using natural gas or natural gas with carbon capture versus coal carbon capture, as well as the green hydrogen production costs. Very energy. All right, so let's talk about the blue hydrogen leaders. For oil and gas industry, it's better suited for them to switch to blue hydrogen versus going with green hydrogen because of their current dependence on hydrocarbon. And so it'd be cheaper for them and just an overall smoother transition. Currently, blue hydrogen projects account for over 130 million tons of carbon capture sequestration capacity, led by North American and African regions due to low costs of natural gas and having oil refining, chemicals industry, and transportation as main demand sectors. And as I previously mentioned, we have several product managers on site, not just for corrosion. But we also had someone from our refining team as well for North America. If you were not able to find me, he would also be a good contact as well. And we are at booth 4308 and 4309 near the food station. And lastly, we do have a blue hydrogen ebook on our Emerson website for more information. I would advise for you to look at that. Emerson has also released a new ebook on reducing emissions and increasing energy efficiency as well. So that's all the slides I have today. Do you have any questions for me?
Are you guys, going to work locations? Like gas plants? Tool stalls?
Well, I specifically focus on the refining industry. So if they're producing gray hydrogen for hydrotreating, hydrocracking, and isomerization, they just would put in carbon capture to make it blue hydrogen. So it'd be an easy transition for them. I know that ExxonMobil has some large projects as well for hydrogen production. I think they're still contemplating if they want to sell it or, just use it as an end user. And a lot of it is being used for ammonia production. If not for ammonia, it's also used for methanol and steel mills as well. I know SoCal Gas is doing that. They are blending hydrogen and natural gas pipelines. They're trying to see what percentage of, these burners that are designed for natural gas, how far they can push that limit, but it is being done. So I would certainly look at what SoCal Gas is doing, because they've actually powered an entire house by mixing hydrogen with the natural gas pipeline. And then I know that power plants are also looking at fueling their current natural gas combustion turbines with a mixture of hydrogen and natural gas. And it can be done. I mean, these combustion turbines already has an SCR system. They won't be able to meet their NOx limits just using ultra NOx burners, but using the SCRs that are already in place, they should be able to meet the NOx standards.
And there's two people from SoCal Gas at this conference this week, so.
That's a 10% hydrogen or 15 that they can put in pipelines. Testing going.
Okay, thank you. If you didn't get a chance to sign in, please sign in before you go. You don't sound nervous. No, very natural. You did a great job.
Good thing is all.
Yeah.